Howdy, my name is Jessica Rion,
Howdy, my name is Diego Reina.
and this is our nanoparticle literature project over biomedicine nanoparticles.
So, in regards to the types of nanoparticles used for biomedicine, in specific for cancer treatment or chemotherapy, we have lipid nanoparticles. And lipid nanoparticles are basically tiny bubbles that are made out of fat molecules. And what's cool about them is that they can carry medicines or genetic material inside them. And so they're basically like delivery trucks for drugs that are used to target these cancer cells. And because they look and act like cell membranes, the body accepts them pretty easily, actually. And so, in regards to how lipid nanoparticles are made, when certain fat molecules, more specific, phospholipids, are mixed with water, they naturally form little spheres. And they can also be created by scientists, through methods like hydration, extrusion, or microfluids. And all of these scientific methods are able to control the size and shape of lipid nanoparticles. In regards to their size, as I was saying, lipid nanoparticles are extremely small. They're usually only between 50 nanometers and a few micrometers. And just for some perspective, a nanometer is a billionth of a meter. So these particles are smaller than even, say, a human cell. Now, talking about why lipid nanoparticles are safe, it would have to be because of their biocompatibility. And when I mean biocompatibility, I'm really talking about how lipid nanoparticles are made from the same kind of molecules in our own cell membranes, which means the body can break them down into naturally harmless substances like fatty acids and glycerol. This overall makes them non-toxic and safe to use for medicine. Now, in regards to how they can be customized, scientists can engineer lipid nanoparticles for specific tasks by either changing their size, modifying their surface, adjusting drug loading, or making them responsive to triggers. And I want to go briefly over every single one that I mentioned, just to explain or elaborate on it further. So, changing their size, you ideally want small nanoparticles because they're going to enter cells more easily. In regards to modifying their surface, you can add tags like antibodies to target cancer cells. Adjusting drug loading, you're basically just controlling how much medicine these can carry. That way, you don't over or underdose the amount of medicine that the patient is going to need for their specific area of cancer. And, in regards to making them responsive to triggers, these lipid nanoparticles can be engineered to release drugs only in the acidic tumor environments or basically wherever the cancer might be present. And so basically, in a simple summary, think of lipid nanoparticles as tiny customizable medicine bubbles because they're safe as they mimic our cells. They're powerful because they can be engineered to deliver drugs exactly where they're needed in the way they are needed. And because and this is why they're being used more and more today for cancer treatments and vaccines. And so moving on into our next slide, which is going to be the application of these lipid nanoparticles. I already touched on some of the ways they're applied in cancer treatment and chemotherapy, but just to reiterate what I was saying and to add on to that, lipid nanoparticles are, like I said, tiny bubbles made out of fat molecules. They can carry medicines inside them and they look like cell membranes. So they can merge with cancer cells and release drugs directly where they're needed. And so this connects to improved targeting because scientists can add tags, like I mentioned, such as peptides or antibodies to these lipid nanoparticles so they can recognize cancer cells. And this means that the medicine is going to go mostly to tumors instead of surrounding healthy tissues. Now, an example you can think of can be lipid nanoparticles delivering chemotherapy or RNA therapy that turn off cancer-causing genes or that boost the immune system. Now, talking about reduced toxicity, traditional chemotherapy hurts healthy cells too, like hair follicles and gut lining. But lipid nanoparticles, on the other hand, protect the drug inside until it reaches a tumor. That way, fewer healthy cells are harmed. And this overall is going to reduce side effects and make treatments easier to tolerate. Now, talking about the enhanced outcomes as a result of lipid nanoparticles, because lipid nanoparticles release drugs at the tumor, more medicine reaches the cancer, and they can even carry multiple treatments at once, like a drug plus gene therapy. And this is just going to lead to better tumor shrinkage, longer remission, longer amount of time fighting against those cancer cells and improve survival. And researchers are, as a bonus, also exploring lipid nanoparticles for personalized cancer vaccines, which further improves the, experience for the patient. And this all really matters because, like I'm saying, right, lipid nanoparticles are precise, with their improved targeting, they're protective with their reduction of side effects, and they're powerful with their improvement of patient outcomes. And this makes them not just useful right now, but revolutionary in the future of modern cancer treatment as well.
So now, how are nanoparticles improved in this application? Nanoparticles can encapsulate and carry chemo or genes. Lipid nanoparticles trap chemotherapy or genetic material inside a lipid bilayer, protecting the cargo in the bloodstream and improving its stability. It also lowers the damage done to healthy tissues. The lipid shell limits direct exposure of organs such as heart, kidneys, the GI tract, etc., to free drug, so more drug goes to the tumor and less to normal tissue, reducing side effects. They also target tumors more precisely. Their nanoscale size and engineered surfaces help them accumulate in tumors and bind specifically to cancer cells. They can also be either enable controlled or triggered release. Lipid nanoparticles can be designed to release their content slowly or in response to tumor conditions such as low pH, enzymes, heat, etc., enhancing therapeutic effect at the tumor site. Now, how does all this improve the current technology for this application? Well, some advantages are lipid nanoparticles being increasing drug accumulation in tumors through enhanced permeability and retention, which can improve anti-tumor efficacy at a given dose. They also reduce systematic toxicity by shielding healthy tissues from high peak concentrations of free drug and altering drug biodistribution. They allow encapsulation of otherwise poorly soluble or unstable drugs, expanding the range of agents that can be used clinically. Some disadvantages, though, liposomal formulations are complex and expensive to manufacture, which can limit accessibility and raise treatment costs. Another one is the drug release and tumor uptake can be variable between patients and tumor types, so not all cancers benefit equally. And some liposomal drugs introduce new side effects and still require careful monitoring. Yeah, okay. So how they improve. Compared with conventional chemotherapy, liposomes provide more targeted delivery and higher local concentrations at the tumor site without proportionally increasing systematic exposure. They also offer longer circulation times and more controlled release profiles, giving steadier therapeutic levels than standard immediate release formulations. As well with surface engineering adds a level of precision and tunability not possible with traditional non-nanoparticle drug formulations. And here are our references. So that was the project. Thank you for listening on the video. Giggle. Should be
Thank
good.
you.
Yes, sir. That should be good.